Hello, my name is John Fiorentino, and welcome to my presentation on using channel state information for tamper detection in the Internet of Things. This presentation was based on the paper of the same title, originally presented at the ACSAC 2015 conference by these authors. This paper was partly funded by the German Research Foundation in the Collaborative Research Center. In the course of this presentation, we'll examine the place of connectivity in the Internet of Things, the real threat of physical tampering with the endpoints and components of this system, a possible solution to this problem in the form of channel state information tamper detection, and the evaluations and experiments used by the authors of this paper to formulate this CSI tamper detection method. Let's move on to the summary overview. With the Internet of Things growing every day, the number of possible security errors is growing along with them. Although many places are isolated, such as air traffic control centers and power plants, the presence of Wi-Fi enabled cameras as well as other kinds of Wi-Fi components in easy-to-access areas can create potential security problems. Because of this, solutions involving leveraging these Wi-Fi systems and components are constantly in the works. The focus of this paper was to identify one such method using Wi-Fi enabled devices using an 802.11n framework. Devices using this framework contain a preamble prepended to each frame of the Wi-Fi data, which contains the channel state information for that frame. This channel state information can include the kind of data that can be used for tamper detection methods, such as the one that will be described here. The channel state information embedded in this preamble can be used to detect tamper events. However, due to the sensitive nature of the components used to detect this CSI, many tamper events, as reported, turn out to simply be environmental changes, including individuals simply walking past the device. Because of this, the method for using CSI in order to detect tamper events is historically unreliable. However, the purpose of this paper is to find a way to use multiple receivers to detect CSI tamper events with more precision and reliability. This was accomplished by implementing a specific tamper detection algorithm and testing this using evaluation methods. In the course of the experiments used to produce this, the proposed system, deployed in a busy environment, was capable of detecting 53% of tamper events while creating 0 false alarms. The threat model in question assumed 3 points. The first being that the type of threat in this case would be physical tampering of the system, not necessarily an electric or software-based attack, more of the device being moved or manipulated in some way so as to limit its functionality in a physical sense. This would be external tampering only, no access to the internal components of the device, and no access or patching of the software. In other words, purely hands-on manipulation of the device. For example, the application in this instance, presented as an example scenario, would be a wireless surveillance system with a Wi-Fi enabled camera in which an attacker would aim to prevent observation of a particular section by moving the camera. This kind of attack cannot currently be detected using the conventional security protocols, so the proposed system would aim to detect these attacks by using multiple receivers to bring in data that would be given off by a specific transmitting device. There has been some related work on the past, the most notable of which is a previous work by some of the same authors of this paper, in which they found a way to transmit location using the same channel state information, which played a very big role in this algorithm, as using the location was a way to determine the tamper states of certain physical components. Aspects unique to this paper, however, are the analysis of multiple scenarios of a more complex nature than the past experiments, the fact that this solution was designed specifically for 802.11n frameworks in orthogonal frequency division multiplexing, and that this project accounts for distinction between environmental and tamper events. Moving on to the actual detection algorithm, it's important to get a feeling for the many different variables and notations that are used to describe this system. The first point in describing this system is to examine using transmit filters to cancel channel effects, also known as beamforming. This is a good early example of the types of notation that the authors used to describe each of these systems. In this instance, the data transmission on each subcarrier, described as SC, is presented as a linear system of R, the received signal, equal to the H, the channel coefficient matrix, multiplied by the transmitter signal T. Instead of directly transmitting a data stream per antenna, the transmitter can decide to use transmit filters to either cancel the channel effects or distribute a lower number of data streams to a higher number of antennae. To perform filtering upon this system, the transmitter uses the filtering matrix F to distribute S spatial streams to T transmit antennas. Here we can see a similar linear system where T from the previous linear system is described as the filtering matrix F by the spatial stream S, all along the same subcarriers. Basic tamper detection is represented as a collection of CSI matrices. The channel state information is stored in a matrix M, and this M is combined as a sum series leading to a total collected and stored over the life of the program. This is usually accomplished in phases, with an early set of data collected during a training phase, which is compared against the live data that is later collected and evaluated in order to try to detect tamper events. In this instance, the total collected and stored channel state information matrices are represented by the Greek letter tau. In order to evaluate distance, 3 different algorithms were applied during the course of this presentation in order to try to find the most reliable way to determine when a physical component had been moved or tampered with. In this case, Euclidean, Mahalanobis, and Earth movers distance were considered, with Euclidean distance being the distance between 2 points direct, Mahalanobis being the distance between a point and a distribution, and Earth movers distance being a distance between 2 distributions. In the course of this examination, it was found that despite having very different implementations, Euclidean, being the simpler, was the best of the 3 to implement, as all 3 distance algorithms had incredibly similar outcomes in the final experiments. The data shown in figures 5, 6, and 7 respectively show the Euclidean, Mahalanobis, and Earth movers data in the initial experimentation. The jumps in the data that occur around the 18.5 minute mark show tamper events for each of the 4 receivers. Because of the similarities and reliability in these systems, despite how much more complicated it is to set up Mahalanobis and Earth movers distance algorithms, Euclidean distance was selected as the distance algorithm of choice for this method. Euclidean distance is defined using the system at the bottom of the screen here, where tau is equal to the series as previously defined, and m is the channel state information. When evaluating tamper events, using multiple receivers, as previously discussed, was the preferred solution, as a single receiver could not tell the difference between an actual tamper event and a false positive brought on by an environmental change. Because of this, it was necessary to devise a certain threshold depicted by lowercase gamma, which could be used as a cutoff to determine the difference between a false positive and an actual tamper event. In this case, if the distance, depicted by d sub I, is less than the threshold gamma, our tamper detection event of lowercase q sub I would return a 0, meaning that our distance had not exceeded the predetermined threshold, and therefore the device had not been moved enough to be considered a tamper event. However, if the distance was greater than or equal to the threshold, gamma, Q sub I would return a 1, and a tamper alarm would be triggered. In order to adapt this for multiple receivers, it was represented as a system of sums, shown here at the bottom with capital Q superscript I, where n is the number of receivers, and all versions of packet I have to be received by all receivers for the decision to whether a tamper event has occurred to actually be made. This provides that extra element of reliability that allows the differentiations to be drawn between false positives and true tamper events. When discussing these metrics and events, it's important to have an idea of what these terms are going to mean. These are used frequently in the graphs and descriptions that the authors provide in their results and experimentation. Specifically, a false positive is when a false alarm is triggered by the system. It reports a tamper event, but the event was not malicious. There was no actual physical tampering with the device. This was when the previous description of environmental changes was brought in, specifically if an individual were to move past the component device, which is important in an environment where there may be many people or even just occasional passers-by moving through the system. A false negative event would be when a tamper event occurred, but the algorithm did not detect it. It was not triggered or flagged as an actual malicious event, and it slipped through the system as a result. True positive was the goal, the success goal for the system, when it would detect an actual tamper event that occurred in real time and successfully report it. Threshold selection is a very sensitive process in this algorithm because it provides the cutoff for what distinguishes a false event from a true tampering event. Because of this, 3 different methods were considered in the evaluations that we'll examine later on. The first was maximum distance. Now, maximum distance would use all CSIs during a training phase and select the maximum move values during this time to be set as the threshold. However, this was found to have subpar results in a dynamic environment. The equal error rate, represented by gamma EER, had low false positives. However, it had also very low true positives, meaning it was detecting fewer true events. This meant that the value itself, the threshold using the equal error rate, was set too high. 0 false negative gave fair true positive rates, but also gave higher false positive rates, meaning the false positive rate was above 0, which was not the ideal outcome for this algorithm. There was no desire to have any false positives being returned. Therefore, 0 false negative was best used when applied with time-wise filtering to bring down the false positive rate. Time-wise filtering is an algorithm we'll examine here in a moment, but it should be noted that time-wise filtering, while pulling down the FPR rate, would also reduce the TPR, meaning there'd be no false positives reported, but there'd also be fewer true events detected. Time-wise filtering is defined by this system of summations, in which Q to the I TW is considered tampered if all individual decisions in the window T sub W were considered tampered. This covers all data points in a full window, meaning that before evaluation could be performed, all frames within that time window would have to be collected and evaluated. And as previously stated, it drags down the TPR with the FPR. So although it makes the 0 false negative method more reliable, it also reduces some of the TPR rates that were the original goal. So although there is no one perfect method, we have a few that perform better under certain circumstances and scenarios, which meant that the algorithm here was better equipped to be set up in the best and most optimal situation. The methods and algorithms previously described were reached using a series of tests and experiments run in this evaluation segment. We're going to go into some more detail about those now. The evaluations were run using the equipment that you see here in Figure 2, a Toshiba NV250-108 laptop equipped with an Intel 5300 network interface card for the experiments. To induce tampering, the antenna shown to the side of the computer was either moved or rotated. All experiments took place in the same location, this series of rooms with a hallway connecting them. The orientation of the components changed. The first experiment, a controlled movement experiment, had this layout as you see here in Figure 3, with the transmitter, designated by the blue T bullet point, appearing in the central lobby, and the 4 receivers, designated by the red bullet points, spread along the hallway. A person, at different phases of the experiment, would move between rooms 1 and room 2, and would interact with the different receivers in a variety of ways to collect the data. The purpose of this experiment was to see if there would be a difference between how the data from when a person would interact with a receiver in a benign way would differ from when an actual tampering event occurred. Figure 4 shows an example of how some of that data might have changed, or did change, rather. Rather, it focuses on more of the appearance. Specifically, T is 3.5 shows the first of the benign movement events, where the person left room 1, walked close to receiver 4, waited next to it for a moment, and then entered room 1 again. In the figure, this affects distance values at receiver 4 very slightly. However, the actual tamper event at 21.5 shows a huge shift in the values, showing that it's easy for this receiver to actually detect a full-on tamper event in these conditions. The controlled movement experiment followed this pattern. At a time of 3.5 minutes, the person would walk close to receiver 4, wait next to receiver 4 for a minute, and then enter room 1. We can see in the figures that this affects distance values at receiver 4 very slightly at receiver 3. Since we do not see any increase on the distance values of receiver 1 and 2, the system will not create a false alarm when considering data from all receivers. Note that figure 5 was what we used before to show the Euclidean distance for the controlled movement experiment. The tampering event at 21.5, as we previously saw, could not be distinguished from the tampering event in the other two distance algorithms that we looked at, Mahalanobis and Earth movers. Another benign event happened at 9.5 when the person would walk close to receiver 3, wait next to it for a moment, and then enter room 1. And again, when there would be no significant change in the receiver values of 1 and 2, no tamper event would be triggered. This was repeated for other receivers at 15.5 minutes and 17.5 minutes. And finally, it ended with the person entering room 2. However, at 21.5 minutes, the person rotates the antenna of the transmitter 90 degrees clockwise and enters room 2. Now the system creates an alarm since distance values for all of the receivers increase. Because of the previous algorithm we examined, where all antenna were summarized together for that capital Q super I variable, tamper events involving all receivers would trigger the event as seen at 21.5 minutes. As previously mentioned, using the multiple receivers to detect tamper decisions is much more accurate. This is the data that led to that conclusion. Figure 8 shows the tamper decisions for the individual receiver in the controlled movement experiment using Euclidean distance. False alarms due to the movement are present throughout at many of the different timed events, including the 18.5 minute event leading up to the 21.5 minute event. However, in Figure 9, the same events charted on the same vertical axis from 0 to 1 show that the decisions were much more accurate, with a tamper event only being triggered at 21.5 as opposed to the several events in Figure 8. For the next experiment, there was an uncontrolled movement phase, where the transmitter was moved into the room, as seen here at the blue T, with the 4 transmitters placed in rooms around them, all connected on the same hallway. People would move into the rooms and the corridor to induce the CSI variations. The experiment would start with the transmitter in a tampered state. The transmitter antenna would be rotated by 90 degrees anti-clockwise from its intended position. After a while, the antenna would be rotated back to its intended position and would then transition to an untampered state. In both states, data for threshold selection would be collected. A history size of tau equals 100 CSI was collected during the untampered state when it could be ensured that the environment would be free of movement. Tamper events during this phase were initiated at specific times during the day. In Figure 11, you can see the tamper events as designated by the vertical dashed lines. These occurred at 2000 hours on each of the 2 days in question. The uncontrolled movement experiment used a large amount of time in order to collect a training phase data. This was so that they could test the 3 methods for determining the threshold that we had previously discussed. The first of those methods, being the maximum distance method, was evaluating using data from the tamper events as displayed in Table 1. The false positive and true positive rates using the max DT method are seen in Table 2, with both nighttime and daytime values being collected. These false positive and true positive rates exist on a scale from 0 to 1. The time ranges for tampered and untampered states for the ROC curve previously mentioned, that being the receiver operating characteristic curve, are all displayed in Table 3. Combining the ROC curve with FNR and the FPR crossover, we can find the EER rate, that being the equal error rate threshold, in Table 4. These were calculated for each of the receivers. Figure 12 shows the ROC curve discussed for those 4 receivers, with Figure 13 showing the FPRs and TPRs for the different phases of the day using each of these 3 methods. Table 5 compiles the resulting values for each of those methods, max, equal error rate, as well as the third one, 0 false negative threshold. 0 false negative threshold, as previously discussed, was initiated in order to get a false negative rate of 0 and was filtered using time-wise filtering in order to reach that 0 FNR rate. Because of this, it also brought down the average true positive rate to 0.53. Despite the maximum distance threshold having a more unreliable aspect in that it cannot be used dynamically, there are some instances in which the equal error rate's low TPR may be acceptable for implementation. Time-wise filtering makes FNR acceptable in many different scenarios simply because it can reach that 0 false negative rate while still allowing the user to capture over half of the true positive events. Figure 14 shows the effect of time-wise filtering on the false positive rate and the true positive rate when using the 0 false negative threshold method. This assumes a time window of 60 seconds to reduce the FPR to 0. Although noted that it reduces the true positive rate, having a false positive rate of 0 cannot be overstated in its value. Figure 15 shows the effect that the number of receivers has on making the decision on false positive rates and true positive rates when using the 0 false negative threshold selection method. From these evaluations and the data derived from them, it was shown that in a setting with limited movement, a perfect scenario for evaluating and detecting these situations could be achieved with a false positive rate of 0 and a true positive rate of 1, with that 0 and 1 being the min and maximum. However, in an environment with a high level of movement, using the 0 negative threshold method we had determined before, it was still possible to get a false positive rate of 0 and a true positive rate of 0.53, meaning that no false events would be detected and reported, and over half of the actual tamper events would be reported. This is the optimum scenario, as determined by these evaluations, for configuring this system, and should be the goal for the implementation of this system. In conclusion, the authors of this paper devised a sophisticated solution that can be applied to directly secure physical components using an existing piece of information in 802.11n CSI frames. This can reliably detect over half of the true tamper events while minimizing false alarms. It can also be noted that this method, although designed for 802.11n networks, can be adapted using the same styles of algorithms to other ODFM devices, simply adjusting for hardware differences. The impact and value of these types of low overhead solutions cannot be overstated, and it can only be hoped that similar types of security solutions are identified in the future in order to help minimize attacks in the public. Thank you for taking the time to watch this presentation. If you're interested in reading the paper from which this information was taken, it's available at the link on your screen.